Shall we start? All right. Hello, everyone, and thank you for the coming to this first seminar, this talk, the first talk for the mSPACE Connected seminar series. It's my pleasure to introduce Gilad Sofer from Technion Israel Institute of Technology, who's going to speak about the Dry Ten Martini Problem for Sturmian Graphs. And this is based on joint work with Ram Band. Before to go to the talk, I just would like to remind you that this seminar, the idea of this seminar is to create some kind of like a connection between different working groups and also to give opportunities to early career researchers to present their works and the work that is being done within their corresponding working groups. So today, Gilad is going to talk about a problem that is in the interest mainly of working group 2, but however, it has connections with other working groups, especially with, for example, working group 1. So, and because the idea of this seminar is that different working groups participate and engage with the talk, I would like everyone who to ask questions in the chat if there is any question that arises during the talk so that we can perhaps read them. And I hope this is okay for Gilad later to ask these questions. Yeah.
Sure.
All right, and so at the end of the talk, we will have also another session for questions. But please feel free to either, for example, just to raise your hand here. There might be one of these options to raise a hand or write any questions that you have during the talk over in the chat. So, okay, so having said, so please over to you, Gila.
Yeah, thanks. So I'm really happy to be the first speaker of this really nice seminar series. As you said, today I'm representing working group 2. I'm also actually in working group 1, but I think that this talk would hopefully resonate with other working groups as well. So as you said, I'll talk about joint work with my advisor, Rami Band, about the Dry Ten Martini Problem for Sturmian Graphs. Before I explain what this actually means, I would like to give maybe a brief explanation of why I think this does relate to the entire cost action and not just for working groups 1 and 2. So we have this very nice name for our cost action, this mSPACE, right? Which, as we know, stands for multi-scale, stochastics, patterns analysis, and combinatorial environments. And actually, as you'll see, all of these words will pop up today. All of these will be very important parts of the talk. To be honest, maybe stochastics, not as much today, but maybe in a different talk sometime. And the idea is that today we're going to be looking at the effect of local patterns on spectral gaps in a multi-scaled structure medium. So already all of these words are coming together. When I say something like multi-scale structure medium, what I want you to have in mind is something like a Penrose tiling or a quasi-crystal or some network of your choice with a very complicated structure. So a space, a large space that is not periodic. It doesn't have this simple translational symmetry, but it does have some underlying global order which governs its geometric structure. So there is some structure behind the scenes. And actually, we'll be focusing mainly on the interaction between the global order of the space and its local geometric features. And we're going to see essentially the main theme of this talk will be that if you look at spectral gaps or of spectral properties in general, then often you have this interesting interaction. On one hand, the aperiodic structure tries to dictate specific features of the spectrum. And on the other hand, the local geometry will try to oppose this and try to force the spectrum to do something else. And precisely this interaction between these two things is what will give us new physical effects that you don't see in one dimension, specifically in the context of the Dry Ten Martini problem. Okay? So I'll talk today about Schrodinger operators on graphs, which is something I know that many people here in the audience enjoy. And a very sort of widely asked question about Schrodinger operators is how does having an aperiodic potential affect properties of the spectrum? So this question has been asked by many people over decades from many different points of view. If you want to talk about localization, about ballistic motion, about many different properties of networks and of spaces, often people are interested in having an aperiodic potential with some nice properties. Today I want to talk about related but different question, and it is how does having an aperiodic geometric structure of your space affect properties of the spectrum? For instance, in the context of this multi-scaled structure medium. Now, as some of you know, aperiodic systems somehow tend to display these really striking and remarkable spectral properties, things like a Cantor spectrum or fractal spectrum, sort of like you see here in the picture, a zero Lebesgue measure spectrum, things that we will see today in the talk, and things that people see in models of quasi-crystals and so on. And I want to look at this from a more geometric perspective. So when you put the aperiodicity in the geometry of the space itself, more precisely, I'm interested in discrete and metric graph models that are generated by aperiodic dynamical systems. So the local geometric structure is governed by the dynamics of some aperiodic system, sort of like you see here in the picture. This is very much motivated by these Penrose tilings, these aperiodic tilings, and the quasi-crystal pictures that we saw before. And we want to talk about spectral properties of those. Specifically in the context of the previous slide, what I'm very interested in is, can you identify which spectral features of these Schrodinger operators on these graphs arise due to the global aperiodic order? And on the other hand, can you identify which of the features actually arise specifically from the local geometry? And of course, lastly, can you identify the interaction between these two things and the total effect that they give together? I think this is a very interesting question to study specifically in the context of graphs. And today we will look at this specifically in the context of the Dry Ten Martini problem of discrete Sturmian graphs. We will study their gap labels. I will shortly explain what this means. But what we will see is that in this problem, you can actually isolate precisely which gap labels arise due to the global order of your space and which gap labels actually arise or don't arise due to local geometric properties. So this will be a nice demonstration of this more general idea that I spoke about before. So I'll start with maybe going back to the world of
Sorry,
one-dimensional Schrodinger operators. Yes, questions?
sorry for, yes, I have just a question regarding this, just perhaps to understand more like the basic objects you are interested in. So could you perhaps remind us what do you mean by what an aperiodic geometry or a periodic dynamical system is?
So when I say aperiodic geometry, I mean it in the sort of intuitive sense that we think about. I think about spatial aperiodicity. So I don't have this natural shift that acts on the space, that I can shift my space by some amount and then I go back to where I started. So when I say that a space is aperiodic, I mean that I can't shift it around and go back to the same pattern that I saw before. In some sense, when I move around, I see something different all the time. But I do have some rule in the background which governs the periodic structure, the aperiodic structure, similar to how you see in aperiodic tilings. Okay, and by aperiodic dynamical system, I think that I will wait one slide further and then I will answer your question. Okay, this will maybe help us understand together through an example.
Okay.
So I'll maybe start from the simplest examples, which are just aperiodic Schrodinger operators on Z. This is something which is has been studied for decades. It is very often very simple to define and very, very difficult to study. And it has many, many interesting properties. So I want to introduce two sort of very famous families of aperiodic Schrodinger operators on Z. Both of those are denoted H alpha, where alpha is some parameter between 0 and 1. usually an irrational number. This is where the aperiodicity would come from. And these operators act on L2 of Z as a nearest neighbor hopping, so just adjacency, plus a potential, and the potential is given by some coupling constant V times a sequence omega alpha n. And the thing that sets apart these two models that I want to talk about is which choice do you make for this aperiodic sequence. So one very famous example is called the almost Matthew operator. And for this, you take the sequence omega to be given by omega alpha n equals 2 cosine of 2 pi alpha n. So alpha here is like a frequency parameter. This strange looking potential actually arises from a two-dimensional model called the Harper model, but I won't get into it. But bottom line, what you can see is that when you take alpha to be a rational number, then you get a periodic potential, which is not really the interesting case. The more interesting case is that when you take alpha to be an irrational number, and then you get an aperiodic operator. And one thing that has made this almost Matthew operator quite famous, this is in some sense one of its simplified forms. In the 1970s, Douglas Hofstadter, who was back then also a PhD student, he decided to plot the spectrum of this operator as a function of the frequency alpha. And what he got was the following really nice picture. This is called Hofstadter's butterfly. And here, the vertical axis represents alpha. And for each alpha, he plotted the spectrum of this operator. And immediately, just visually, you start asking questions, right? Where does this fractality come from? What can you say about the spectrum just by looking at the picture? Many interesting questions that people have been studying for decades, many open problems also today. This is arising from this very simple choice of the aperiodic potential. And another very important family that I actually want to focus on even more today is the family of Sturmian Hamiltonians. And for those, you take an even simpler aperiodic potential. You take the potential to be given by omega alpha n equals a characteristic function from 1 minus alpha up to 1 of n alpha mod 1. So this potential only takes on two values, either 0 or v, this coupling constant. And now, if you go back to the question about where does this aperiodic dynamical system comes from, we can try to visualize this potential using the following dynamical system, namely an irrational rotation. So if you want to visualize what this potential does, you can think about taking some irrational angle alpha. You take an alpha-sized sector in the unit circle, and you look at the associated irrational rotation. So this is the aperiodic dynamical system in the background, and you use this aperiodic dynamical system to define this simple potential. And even though this is a very simple aperiodic potential, it is already enough to introduce some really interesting spectral properties. Similar to the almost Matthew operator, you can also plot the spectrum of Sturmian Hamiltonians as a function of the frequency alpha, and you get, once again, this interesting fractality phenomenon, which gives rise to many interesting questions. And once again, I emphasize that even for these very simple models defined by this very simple aperiodic dynamical system, you already see very interesting spectral properties. So some very fundamental problems that people were wondering about when these models were just introduced. One of them is known as the 10 Martini problem. So this is a problem that allegedly Mark Katz suggested back then, and he offered allegedly 10 martinis to whoever is able to solve it. And the idea is that you want to show that the spectrum of these operators, H alpha, is a Cantor set for all irrational frequencies. So this is somewhat trying to address part of the fractality that you see in the picture, at least on the level of horizontal cross-sections, on the level of each individual spectra, you get Cantor sets. So this is the 10 Martini problem. And even though it is very simple to state it, it's a bit tougher to answer it. So for Sturmian Hamiltonians, it was answered in 1989, and it was shown that indeed the spectrum is a Cantor set. For the almost Matthew operator, it took quite a longer time. It was only answered in 2009. by Artur Avila and Svetlana Zhitomirskaya after other advances by additional people. And there as well, it was shown that the spectrum is a Cantor set. Both of these results together are really important landmarks in studying these operators. So even proving these very fundamental properties about the spectrum took a lot of effort because studying aperiodic systems is complicated. You don't have Floquet-Bloch theory, so this was already an important landmark. And this was the Ten Martini problem. But
Sorry,
yeah,
I have another question. Yeah,
uh-huh.
so about this plot, so how can we understand then these pictures? So how can we read them?
Yeah, so this is the million-dollar question. How can you understand
Yes.
this spectra? So let me go back to the previous slide. Here you see two axes. So the first axis is the alpha axis. This is the vertical axis. For each choice of the frequency alpha, you plot the spectrum of this operator. And when you look at the entire picture, not just the individual spectra, but all of the spectra put together with different frequencies, then you see that there is some underlying structure governing everything. It's very hard to identify and say precisely what it is, but you can see that something interesting is happening. So this is a lot of the things that attracted initial attention towards these models. Okay?
Okay, yeah, so okay, there is a question also here in the chat.
Mhm.
And the question is, why is this called Ten Martini problem?
Because allegedly, but I think it's actually true. Mark offered 10 martinis to whoever is able to solve this problem. He originally asked it about the almost massive operator. It was later asked also for Sturmian Hamiltonians. If you solve it, you get 10 martinis. This is the deal. Although I think it was only solved after Mark passed away, so I don't think anybody actually got 10 martinis, to be honest. But still, it's a very nice problem. But it turns out, if we go back to what Markatz originally asked, it turns out that he then didn't actually ask about Cantor spectrum. So if you go back to Markatz's original question, it turns out that he asked something slightly different, and this is sometimes known as the dry version or the Dry Ten Martini problem. And the question is, do these operators have all of their gaps? Are all of the gaps of the operator actually there? And this is a more subtle question. And what did he mean when he asked this? What did he mean by does an operator have all of its gaps? For this, I need to introduce something called gap labels. This is the main thing that I need to introduce for this talk, namely the integrated density of states that some of you may know from statistical mechanics and solid state physics. And the idea behind the integrated density of states, or IDS, is that even though my operator is defined on all of Z, I can always restrict it to a finite patch of size n, and then I just have an n by n self-adjoint matrix, and I can study its eigenvalues. Namely, I can look at its normalized eigenvalue counting function. So I normalize by the size of my box, and I have this step function that counts how many eigenvalues I have below a given energy. And the idea behind the integrated density of states is that I'm going to take the size of the box to infinity. And what you can show is that as you take the size of the box to infinity, the sequence of step functions actually converges to this devil staircase type function, which we call the integrated density of states of the system. So sort of heuristically speaking, it counts how many states you have per unit volume below a given energy. But of course, the limiting operator doesn't have to have a discrete spectrum at all. Usually it doesn't have it. So it's sort of a generalization of the counting function for this aperiodic system. And here are some basic things you can show about the IDS. First of all, it is a monotone non-decreasing function as the limit of such. And more importantly, it is constant inside spectral gaps. So what I mean by this is that if I have an energy outside of the spectrum, then there is some neighborhood of this energy where the IDS doesn't change. It is constant. And so essentially in this picture, the flat regions correspond to regions outside of the spectrum or spectral gaps, components outside the spectrum. And if you combine these two properties together, what you see is that you can essentially identify between the spectral gaps of the operator, so components outside of the spectrum, with the value that the IDS attains inside the given gap. So you identify each gap with the value that the IDS attains inside it, and you call this number the gap label. And often people are interested in the overall collection of gap labels of an operator, both because it has some physical meaning, and also you can use it to classify some properties of the operator. Usually the game in physics, in solid state physics, and also in spectral theory, you give me an operator and I want to compute its gap labels. And of course, the almost Matthew operator and Sturmian Hamiltonians are no exception. People want to compute their gap labels. And a very important result in this regard is called the gap labeling theorem, which was proven actually for both of these systems. And it says the following. It turns out that the collection of gap labels, the collection of values of the IDS inside spectral gaps, is contained in the following interesting set. All of the numbers of the form n alpha mod 1, where alpha is my irrational frequency from before, and n is some integer. So there is a very strong sort of arithmetic structure which governs the gap labels for these models. And now when Mark Katz asked, does the operator have all of its gaps? What he meant was, do you have equality here? We know that all gap labels are of this form, but are all numbers of this form actual gap labels attained by the IDS? This is a different question. And it turned out to be quite a difficult question. It still is a difficult question. It has remained open for several decades. And only recently, I mean, there has been many interesting advances towards it over several years. And recently it has been resolved almost completely for both of these operators. So for the almost Matthew operator, the problem was resolved in 23 by Avila, Yu, and Zhao for almost all values of the potential, except for v equals 1, which remains a very, very difficult and interesting open question. And for Sturmian Hamiltonians, it was resolved in 24 by Band, Beckus, and Levy for all values of the coupling. And in both cases, it was shown that Mark Katz was right. All gaps are there. The operator has all of its predicted gaps as predicted by the gap labeling theorem. But this is a result that took decades to reach. For the almost Matthew operator, it is still somewhat open. And this is very much a motivation to what I'll be talking about today. But as I said, today I don't want to look at potentials. I want to move to a geometric problem. So we will try to define a geometric version of the Dry Ten Martini problem using graphs. So we're going to implement this aperiodicity inside the graph structure.
Sorry,
So,
Delio.
yeah?
Sorry for interrupt. Delio?
Thanks. May I ask a question, Gilad?
So that
Sorry.
Okay.
May I make a question to make it maybe more accessible to a casual audience. So if you show the plots again, can you detect the gaps just by looking at the plot?
So you're looking at the fractal plot from before.
Right.
So this is a really good question, actually.
Thank you.
Yeah, sure. So can you somehow see, so you see that there are gaps in these butterflies, but can you identify which gap in the butterfly corresponds to which value of n alpha mod 1? This is your question.
Yes, exactly. So first of all, is it clear that these white regions, like I guess it is the white horizontal regions that are the gaps, right?
Right, exactly. Each horizontal cross-section is a spectrum of a different operator with different alphas, and the white regions are regions outside the spectrum. These are the spectral gaps. Can you see from this picture the gap labels? Naively, no. But actually, there has been some really interesting advances towards this, especially recently. For instance, for Sturmian Hamiltonians, there is a recent interesting work by Band and Beckus where they really try to read the gap labels from this butterfly picture. This is extremely interesting. I won't be talking about this today, but this is a really good question.
Maybe just because we are at it and we are showing this picture. So maybe can I ask you once again? So okay, you explained what is the y-axis, so the yeah, but what's on the x-axis? So how broad are these pictures?
So
is it
all of
minus
these
1, 1?
Yeah,
they
so all of these
normalized?
operators are bounded, and actually the precise bounds depend on the coupling that you pick. So if you take the coupling to be zero, you just have a free Laplacian. So you have spectrum between zero and two, or depending on which
Well, sigma
convention you
minus
pick.
1, 1, I
Yeah,
guess.
yes. And for different values of the coupling V, the spectrum sort of moves around.
Mhm.
So this is essentially the idea. But all of these operators are bounded. So
And
you,
same for
you
the
are
Sturmian
restricted.
Hamiltonian. Yeah.
Good.
Okay, thanks.
Sorry,
So,
one
yeah.
question. So in these pictures also you are plotting the alphas which are rational, or is it just like other ones?
Oh, this is also a really good question. Actually, I mean, naively, it
Mm-hmm.
is impossible to plot things for irrational alpha because for irrational alpha, the spectrum is actually a Cantor set. So you can't really plot it. The way that you produce these plots, and this is actually exactly what the Hofstadter originally did, you plot it only for rational alphas. And for rational
Okay.
alphas, you can study it using Floquet-Bloch theory because these are periodic operators. And
All
you
right. I
take
see.
many, many rational alphas.
Mm-hmm. Okay.
Okay?
Thank you.
Perfect. And this will actually be a key point in how we study these operators later on.
Mm-hmm. Mm-hmm. Okay.
Perfect. So let's go back to graphs. Finally, we can talk about graphs. So we want to do a geometric version of this Dry Ten Martini problem for Sturmian potentials. We're going to define a Sturmian decorated graph. Today, I'm only going to be taking discrete graphs, although we can do metric graph analogs of this. So how does this work? I choose my two favorite discrete graphs, finite. I call them A and B. I take my irrational rotation from before. I get this Sturmian sequence of zeros and one. And I decorate the line using my graph. So whenever I land inside the white region in this irrational rotation, I put a graph of type A. Whenever I land outside in the blue region, then I put a graph of type B. And I get this sort of very simple geometric analog of a Sturmian Hamiltonian. And I want to ask spectral questions about it, even for the simplest models I can think of. Today I'm going to make things even simpler for everybody. I'm going to take my graph to be what I call a Sturmian comb. My decorations are going to be either this dangling edge or just a vertex, nothing. This is the simplest aperiodic geometric model you can think of. In the end, I will say how you generalize, but for simplicity, let's focus on this. We have this aperiodic discrete graph. We equip it with the adjacency matrix. Again, this is for simplicity. You can take essentially whichever operator you like. You can take normalized discrete Laplacian. You can take Jacobi operators. And actually, you can also do, as I said, a metric graph version of this. But we're going to take the simplest thing that you could take. We ask spectral questions about it. Namely, we're going to talk about the Dry Ten Martini version in this geometric setting. So let's maybe talk briefly about actually the Ten Martini problem for this model, just because it's interesting. This is something that we worked on a while ago, and what we can show is that up to a finite set of isolated points, the spectrum, similar to the usual Sturmian Hamiltonian, is a Cantor set of Lebesgue measure zero. So we can also plot this version of Hofstadter's butterfly for this model, and we see that once again you have this fractality, you have this Cantor spectrum. And now the natural thing to ask is, if you have 10 Martini, do you have the Dry Ten Martini problem? Are all of the gaps there? And this is what I want to focus on. So as we saw before for the classical Dry Ten Martini problem for Sturmian Hamiltonians, we saw that all gaps are there. The set of gap labels is precisely what the gap labeling theorem predicted, numbers of the form alpha n plus m, where m and n are integers inside 0, 1. Now, before we ask whether all gaps are there for the geometric system, we first need to have a gap labeling theorem, right? We need a list of candidates and ask whether all of the gaps are there. So the first thing that we did was to prove a gap labeling theorem for this system. And it turns out that the result is very similar to the usual Sturmian setting. It turns out that the gap labels are contained in the following set. All of the numbers of the form alpha n plus m, where alpha is my irrational rotation, m and n are integers. It turns out that now I have a geometric normalization, 1 plus alpha. This somehow comes from the local structure of the graph. But we see that at least on the level of algebraic structure, the aperiodic rule gives us the same structure for the gap label. So this, once again, relates to my first slide. Because we have the same global order governing this graph and the Sturmian Hamiltonians, the gap labeling theorem tries to have a similar set of gap labels, at least on the level of their arithmetic structure. And now the Dry Ten Martini question is, do we have equality? Is this the precise list of gap labels for these graph operators? And here is the point where the graphs start behaving differently. So what we see here is something new. Unlike the one-dimensional case, not all gaps are there. There are many missing gap labels. And it turns out that the collection of open gaps, collection of obtained gap labels, depends on arithmetic properties of the frequency alpha, namely on its continued fraction expansion. And this is something that you don't have at all in the one-dimensional case. So let me state this more precisely. So let A1 be the first digit in the continued fraction expansion of alpha, my frequency. Then the set of gap labels for the Sturmian comb is given by the following set, and I'm taking a dramatic pause because this is going to be a long formula. All of the numbers of the form alpha n plus n divided by 1 plus alpha, as we expected before, but not all of these values, not all of the possible values, only the values inside these two intervals. And these intervals depend on the first continued fraction digit, namely on its parity, whether it is even or odd. For both these cases, you get a different set of gap labels. So I don't want you to stare too long at this formula. It's a long formula, but what I want you to have in mind is that all of the gaps, all of the expected gaps are there, except for one interval in the center of 0, 1 of missing gap labels that are not obtained. And I don't want to give you the proof. It's a long proof, it's very technical, but what I want to do for the remainder of the talk is to give you the idea of why that is. And by why that is, I mean two things. First of all, why do the gap labels look so similar to the usual Sturmian setting on one hand, and on the other hand, why are they different? Why are there so many missing gap labels? And this will actually go back to my original slide of this interaction between global order and local geometry. Okay? So to understand why this result holds, we need to understand the notion of periodic approximations, which is actually related to the question asked before. The idea is that it's really hard to study aperiodic operators, but periodic operators are much more accessible. So we're going to, instead of looking at the aperiodic operator, we're going to define a sequence of periodic approximations. So instead of we're going to take our irrational Sturmian frequency and write it as an infinite continued fraction expansion. Now, even though it's an infinite expansion, we can always truncate it after n steps. This will give me some rational number, alpha n, which approximates my irrational number. And because this rational number corresponds to a periodic graph, then we can, from this aperiodic graph, we can get a sequence of periodic graph operators. And those guys we can study using Floquet-Bloch theory. And this is really the heart of how we try to compute the gap labels. And this actually is also what people do for the strictly one-dimensional systems. So here are some basic things we can show about these approximants. First of all, each periodic approximant has finitely many spectral bands. Of course, these are bounded periodic operators. They have band gap structure. So here I plotted for you the first several periodic approximants. And what we see from the picture is that as n becomes larger and larger, as we take a better and better approximant, the bands split into smaller and smaller bands in some interesting pattern. And the idea is that we want to use this idea to compute the gap labels. So for each periodic approximant, we have band gap spectrum, the bands split. And what you can show is that as you take n to infinity, you can, in some sense, obtain the aperiodic graph spectrum from the sequence. I won't be too precise here. I won't explain precisely how, but you can use this sequence of spectral approximants to really get at the limit the spectrum of the aperiodic operator. So you get a lot of information from this periodic data. And our goal for solving the Dry Ten Martini problem is the following. We want to show that the periodic approximants for these graph operators, in some sense, behave similarly to how the periodic approximants behave for the usual one-dimensional Sturmian systems. In some sense, we would like to show that this splitting of spectral bands follows a similar pattern, and this will give us the reason why the gap labels behave so similarly between these two systems. Okay, and we're going to use this to compute the gap labels. To do this, we need one less technical tool, which is called transfer matrices. This is something that we use to compute the spectral periodic approximants. And this is really the heart of why the graphs behave so similarly to the one-dimensional system, because of these transfer matrices. So let me introduce what those are. So we fix some spectral parameter E in R, and we consider the eigenvalue equation of the adjacency matrix on this aperiodic discrete graph. It's a second-order equation. We can solve it, and we can denote the values of the solution psi at the base of these different decorations by psi n plus 1, and so on. And because this is a linear second-order equation, what we can show is that the decoration that I put at site n actually determines a unique matrix, which I denote MAE. It depends on the decoration A and on the energy E that I fix, such that the following holds. If I take this matrix and I apply it to this vector of values psi n plus psi n minus 1, it propagates me one step forward to psi n plus 1, psi n. So this matrix is called the transfer matrix because it transfers me one step forward. And for instance, for the Sturmian comb that we saw before, we can actually write down explicitly what these matrices are. This is the transfer matrix of a trivial decoration when you put nothing. This is the transfer matrix of a non-trivial decoration where you put a tooth. In general, for whichever decorations that you pick, you get some very neatly computable transfer matrices. Now, you can use these transfer matrices to compute the band spectrum of the periodic approximants as follows. So given my periodic approximant, I can multiply the transfer matrices of all of the decorations inside my fundamental domain across the entire period. And this compound transfer matrix gives me the propagation along the entire unit cell. And you can use this compound transfer matrix to compute the spectrum of the periodic approximants using the following very standard result from Floquet-Bloch theory, that an energy belongs to the spectrum of my periodic approximant if and only if I take the corresponding transfer matrix, I compute its trace, and if its absolute value is less than or equal to 2, then this energy belongs to the spectrum. So I can actually use this to compute the band gap spectrum from before. How do I do this? I take some periodic approximant, I compute its transfer matrix, I plot the trace of this matrix, and whenever it lands between -2 and 2, these regions are precisely the spectral bands for my operator. Okay, so this is how I compute this splitting band structure that we saw before. Now comes the interesting part. This is all something that you can do for both graphs and also for operators on Z. And now we will see the relation between the two. So if I go back to the usual Sturmian Hamiltonian with a coupling constant V, then I can write down its transfer matrix, and it is given by these two possible matrices. This is the trivial one on the left, and on the right you have the non-trivial one. Now let me write again the expression that we saw before of the transfer matrix for the Sturmian comb. And now I want you to have a look at these formulas for 10 seconds. And you will notice that these formulas actually look very, very similar to one another. So the trivial transfer matrix is the same for both systems. And the non-trivial transfer matrices, I mean, they're not the same, but they look very similar to one another. One depends on the coupling V, and one depends on the energy of this 1 over E. And our idea is going to pretend that they are the same thing. We're gonna replace my tooth decoration with an effective coupling, which we're going to take to be equal to 1 over E. So this is not an actual coupling constant because coupling is just a constant number. It is energy dependent. But the idea is that for each energy, we're going to pick a different Sturmian Hamiltonian with different coupling. So actually, if we fix some energy, E0 in R, it's just a number, we fix it, then we can consider the associated Sturmian Hamiltonian, where instead of arbitrary coupling V, I take my coupling to be equal to 1 over E0. And the magic happens here. If I look at energy E0, then at this particular energy, the two models have the exact same set of transfer matrices, meaning that at this particular energy, the spectral bands for the two operators look very similar to one another. And our idea is to actually use this to show that the periodic approximants for both of these models locally behave the same. So what we can show is that, in fact, because the transfer matrices are the same, E0 will be in the spectrum of my adjacency matrix of my graph operator, if and only if E0 is in the spectrum of the Sturmian Hamiltonian with coupling V of E0. So for each energy, I can assign a different Sturmian Hamiltonian, which gives me through the spectral correspondence the spectrum of the aperiodic graph operator. So I'm using something that I know about one dimension in order to say something globally about graphs. So let's try to visualize what this spectral correspondence actually looks like. So to do this, I'm going to plot the spectrum of the usual Sturmian Hamiltonian. So I fix now alpha, I fix the frequency, and now I plot for you a different butterfly. I fix alpha and I plot the spectrum of the usual Sturmian Hamiltonian on Z as a function of the coupling constant V. And we know that E0 is in the spectrum of the graph operator, if and only if E0 is in the spectrum of the Sturmian Hamiltonian with coupling 1 over V. And what does this tell us geometrically? Is that I can think of the spectrum of the Sturmian graph as a cross-section of this butterfly picture. I consider the curve V of E equals 1 over E, and whenever this curve intersects this butterfly, if I take the associated energy, if I project everything onto the energy axis, then I get precisely the spectrum of the graph. So actually, we can think about the geometric problem, the graph problem, not as one specific Sturmian Hamiltonian, but we can think about it as an entire cross-section of infinitely many Sturmian Hamiltonians. And if we know something about each individual Sturmian Hamiltonian, then maybe we can say something interesting about the entire graph model. And this is really the heart of why the two problems look so similar in terms of the actual result. This is very delicate. I'm not going to the technicalities of what precisely you show here, but this is heuristically the idea of why the two models are related, precisely because of this cross-section picture. We know that at each fixed energy, the classical Sturmian gap labeling theory applies. So the idea is that we can actually show that locally the gap labels for both models behave very similarly. And naively at this point we are done, we should be finished, right? Because the two models behave locally the same. But now the problem arises. We have this spectral correspondence, which uses this effective coupling, which equals 1 over E0. And if you see 1 over E, then you should also already be suspicious. This correspondence fails at one very particular energy, namely at energy 0, right? At energy 0, there is no 1 over E. And actually, what you can show is that at this particular special energy, the spectral correspondence doesn't apply anymore because the transfer matrix is not defined. And this is precisely where the geometry reappears. This is precisely the thing that stops the geometric model from behaving like the one-dimensional model. And this will actually precisely be the source of the missing gap labels. So how does this work? So we saw that the two models behave similarly away from energy 0. So what causes the difference? The difference is caused due to compactly supported eigenfunctions or flat bands. This is something that does not exist in one dimensions. It only exists in spaces without existence and uniqueness, like aperiodic tilings or like graphs, as some of you know. Graphs don't satisfy existence and uniqueness, and this gives rise to the possibility of having compactly supported eigenfunctions. And what is the effect of these compactly supported graph eigenfunctions on the gap labels? Well, what you can show is that precisely at energy 0, where the spectral correspondence fails, the geometry does give rise to compactly supported eigenfunctions. And then what happens? If you have a compactly supported eigenfunction, you actually have infinitely many of them, because you can take one compactly supported eigenfunction, you can shift it around, and what you can show is that you have infinitely many of those. So you have an infinitely degenerate eigenvalue. And what happens to the IDS when you go near a very highly degenerate eigenvalue, where because the IDS is essentially a counting function, it's a generalization of the counting function, once you reach energy zero, you have so many eigenvalues that the integrated density of states doesn't have a choice but to have a jump discontinuity. So it goes up, then it reaches energy zero, and all of a sudden you have so many flat bands that the IDS actually jumps. And now what happens? Well, the gap labeling theorem predicts many, many gap labels here in the middle, but by definition, we are jumping over them, we are missing them. So this geometric mechanism, these compactly supported eigenfunctions actually make you lose many, many gap labels. All of the gap labels here will be lost. And this is the precise thing that doesn't happen for one-dimensional systems. So what we can show is that as the IDS has a jump, it skips an entire interval of predicted gap labels. And actually, we can show that this jump discontinuity depends precisely on the first continued fraction digit of the Sturmian frequency and its parity. So I won't go into the specific reason why, but you can show that the amount of compactly supported eigenfunctions that you have depends on this arithmetic property of the frequency. So for instance, here you see a plot for an odd continued fraction digit. Here you see an even continued fraction digit, and what you see is that the structure of the spectral approximants is different. And this is precisely the thing that governs the amount of eigenvalues that you have and the size of the jump. So away from energy zero, everything is perfect. The graphs and the Sturmian Hamiltonians behave very similarly because of the global aperiodic order. But at zero, we have this IDS jump because of this geometric mechanism. So let me summarize everything that we saw today. So on one hand, we have this quasi-periodic structure of the graph, and it really tries to force all of the gaps to be open. Why does it force the gaps to be open? Because away from energy zero, you have the very nice spectral correspondence that we saw using this cross-section. So all of the gaps want to be open. But on the other hand, you have this opposing force. The local geometry wants you to have compactly supported eigenfunctions. It wants you to have a jump in the IDS. And this is precisely the thing that makes you lose so many gap labels. So what we saw is, for the bottom line, is that for graphs, not all predicted gaps are there, unlike the one-dimensional case. And this takes me back to the original slide that we did in the beginning. What we see is that the aperiodicity can predict, it can try to force the spectral structure, but on the other hand, only the geometry will decide what survives in the end, which gap labels survive. So today I spoke about this in the context of the Dry Ten Martini Problem, but actually we also, in the context of the Ten Martini Problem, you can see the same problem. You can see it from many different perspectives from this model. Anytime the global order wants the spectrum to do something, and the local geometry tries to resist and do something else. So I spoke today about these Sturmian combs of the adjacency matrix. As I said, you can extend this to many other models. You can take different decorations. You can take different operators like Jacobi operators that normalize discrete Laplacian. You can take equilateral metric graphs as well. And the same result will hold, meaning that all gaps are there except for the ones that arise due to flat bands. We are currently also working on extending this to non-equilateral metric graphs, but this is more complicated, and there I actually suspect that the result may be slightly different. This will maybe be a future talk. In general, let me say that my long-term goal is to be able to extend this general idea of using what we know about one dimension in order to say something about a non-trivial geometry. So as some of you may agree with me, you can often think about graphs as sort of a bridge between something one-dimensional and something higher dimensional. Our long-term goal is to be able to use this idea in order to say something about systems with an even more complicated geometry in higher dimensions, but this is very much an open question that I'd be happy to discuss. Before I thank you for your attention, I want to take one more moment, 1 minute, for a small personal note and do a bit of a self-promotion, a shameless self-promotion. I want everybody to know that I'm actually looking for a postdoc position starting October 2027. I'm very interested, as you see, in graph operators, in spectral geometry, in models for mathematical physics, and in general, everything that we study here in the different working groups. If you have a position or if you know someone who has a position, please feel free to reach out to me. And with this, I'd like to thank you for your attention, and I'm open for questions.
Thank you so much, Gilad. Is there any question for Gilad? No?
Maybe a small question
Yeah, please.
about the convergence of the rational approximations.
Yeah.
Do you have convergence in a Hausdorff sense of the spectrum?
Yeah,
Or is
so
it
what you
something?
can what you can show is that if you interestingly look at the union of each two consecutive spectral approximants, so maybe the union of the first and the second, or the second and the third, if you look at this sequence of unions of spectra of two levels, and you look at this sequence of closed sets, then at the limit, in the Hausdorff sense, you have convergence of these sets to the actual spectrum. So there are also other notions of convergence here, but one of the most interesting ones is that you have actually, well, Hausdorff convergence, and you have this actually also for the metric graph models, which is remarkable because the operators are unbounded. These are not compact sets, but still you have Hausdorff convergence here.
Any other question? Well, I do have questions. So first, yeah, this is a very interesting problem. So it connects very different areas. In particular, my background is a bit on geometry and topology, and a bit of actions of groups. And because you were talking about like a local geometry, it seems to be like some symmetries there appearing, and I guess that there should be some kind of connections with when you were saying about the words and so on, something related to group theory and like how this might affect. So have you thought of these connections related to like with group theory?
Yeah, so group theory definitely enters in a lot of different points here. I have to say that I'm not a group theorist, but I do enjoy the fruits of the interesting group theory that arises here. For instance, if you look at this set of gap labels, right? This is the gap labeling theorem. So actually, in order to give this prediction of the gap labels, you need to use some group theory and topology and dynamical systems. Namely, you show that the possible set of gap labels has this interesting group structure. So you need to go back to the Sturmian dynamical system. By Sturmian dynamical system, I mean this irrational rotation. You can associate with this dynamical system a topological space, namely the suspension space. And the suspension space has a fundamental group. And actually, this is all very abstract, but what you can show is that the gap labels are in some sense correspond to homotopy classes in the fundamental group of this dynamical system in the background. So it all starts from having a group action, this Z action on S1, and then you can really lift it up and use it in order to show that in some sense, in some abstract sense, the gap labels are all hiding inside the group structure of the fundamental group of this space. This is super interesting. I'm sure that there are other interesting connections there, but this is the main thing that comes to mind.
Right. Yeah, and so perhaps my other question related to that is I thought that maybe that's why, or why is that you decided to study this Sturmian graphs? Have you thought of where the idea came from, and if you have thought of other type of graphs that behave similarly to these ones?
Yeah, so the Sturmian structure is really vital here. The general question of why people like these Sturmian sequences, well, in some sense, you can show is that these Sturmian sequences, these aperiodic sequences, are in some sense the simplest aperiodic models that you can take. These are the models that are, on one hand, they are aperiodic, on the other hand, they have very low complexity. So they are in some sense more easier to study. Of course, they are very not easy to study, but even this very simple aperiodicity gives rise to very complicated properties. But we do use very fundamental properties of this Sturmian dynamical system. What here can we extend to other dynamical systems, more complicated dynamical systems? This is the million-dollar question. Currently, it is not clear. This is one of the main things that we're trying to understand now. What elements of this picture, of this picture, can we move to non-Sturmian dynamical systems? We're not sure yet. I think that you can use this idea to study other dynamical systems as well, but it's much more complicated, and we are trying to understand now how far can you take this idea. I think there is a lot of potential there.
All right. Oh, thank you very much. And I think Daniela has a comment, very interesting one. Sorry. Yeah, so you put a comment
Thank
in
you.
the
It's just a comment. I mean, I haven't came up with smart questions. Yeah, currently I'm actually trying to study some models of aperiodic structures that are like random, right? And there are some very interesting features. So we are not that far to study actually things like spectra and so on. But eventually in the future, this would be a very, very nice direction. So if ever you are interested in putting some randomness inside your computations, I mean, you can let me know, definitely.
So as I said in the beginning of the talk, so far I didn't take stochastics into account, but
Yeah,
this is
that
by
hurt.
far
That actually hurt.
Yeah, I'm sorry about that, but this is a really interesting question because actually once you introduce randomness in aperiodic spaces, then you do have very interesting phenomena like localization and all of these really interesting things that we don't have for these systems. So actually, it will be really interesting to see how these models behave.
It's
Again,
true,
it's
but
a direction.
yeah, I mean, but what you showed, the transition matrices, the models, it just looked to me like normal Markov chains. So actually, yeah, so we have a lot of tools to actually
Right.
fit to your computations.
Yes, I think there are many tools from both of these works that can be applied
Yeah.
to both of these systems. So I
And
think
this
this
would
is a
be a
really
nice
interesting
fusion
direction.
eventually.
Yeah, for sure.
Yeah.
Thank you, Daniela. And Delio, you have a question, right?
I had a small technical question, but perhaps I can ask Gilad then in private. It is much less ambitious than this smart question that were asked before, so maybe it's not worth in this circle.
All right. Well, if you are shy enough, then we can just maybe say, Gilad, thanks again. Let's unmute our and say thanks again to Gilad. All right. Thank you very much. I think with this is the end of our first talk. I hope you have enjoyed and that we can continue with these seminars. We are going to have a break for the summer, but please stay in touch so that we can meet again for the next seminar. Thank you very much. Thank you, Gilad.
Thank you.
Thank you. See you.
Thank
Bye-bye.
you.
Bye-bye.
Bye. Bye.